Now, IPv6 is the successor to IPv4, and it offers a lot of benefits over its predecessor. The first major improvement that came with this new version is that there's been an exponential increase in the number of possible addresses that are available. Several other features were added to this addressing scheme as well, such as security, improved composition for what are called unicast addresses, header simplification and how they're sent, and hierarchical addressing for what some would suggest is easier routing. And there's also support for what we call time-sensitive traffic, or traffic that needs to be received in a certain amount of time, such as voice over IP in gaming. And we're going to look at all of this shortly. So the IPv6 addressing scheme uses a 128-bit binary address. This is different, of course, from IP version 4, which again uses a 32-bit address. So this means, therefore, that there are 2 to 128 power possible addresses, as opposed to 2 to the 32 power with IP address 4. And this means, therefore, that there are around 340 undecillion, I'm going to write that out, so that's a word that you probably haven't seen a lot, undecillion addresses. And to put that another way, it's enough for 1 trillion people to each have a trillion addresses, or for an IP address for every single grain of sand on the earth times a trillion earths, give or take a bit. So if the 128-bit address were written out in binary, it would be 128 ones and zeros, because that is binary. And even in decimal form, that's pretty hard to read and keep track of. So because of this, we use what's called hexadecimal as the format in which IPv6 is written. And if you imagine from the name, binary is a base 2 system, meaning that we take everything to the power of 2. So we have the ones place, and then we have the 2 place, and then we have the 4 place, and so on and so forth. With decimal, which is a base 10 system, we have the ones place, the tens place, the hundreds place, which is 10 times 10, the thousands place, and so on. With hexadecimal, though, we're looking at a base 16. So every single digit has a possible 16 different options. So we'd have a ones place, which we always start with a ones place, and then a 16s place, and then so on and so forth. Now, the way we do this is that every digit, as opposed to decimal, where we have 0 to 9 options for every digit, and binary, where you have either 0 or 1, with hexadecimal, we can either have 0 to 9 or A through F. If we add this up, we have 10 options here, 0 through 9, and then A through F, we have 6. So a hexadecimal number is going to be a combination of anywhere from 0 to F. A would be 10, B would be 11, C would be 12, and so on and so forth. So when you see this written out, that's what that means, okay? Now, the address is broken up into 8 groups of 4 hexadecimal digits, and these are separated by colons. Now, I'm going to show you this in just a second, but there are also a couple of rules when it applies to when we come to readability. So the first rule is that, let's say this is our hexadecimal IPv6 address. You notice, first of all, 1, 2, 3, 4, 5, 6, 7, 8, right? There are 8 groups of 4 hexadecimal digits each. And, of course, each one of these digits has 16 possible values. Okay, so let's look at 2 rules. And these are also not only readability rules, but what we call truncation rules, meaning this is how we can shorten an IPv6 address, since they can get quite long. The first rule is that any leading zeros can be removed. So if we imagine any leading zeros, I'm going to circle them right there, right here, right here, and if we wanted, we could even consider these leading zeros. And therefore, if we rewrite this out below, you'll see we're going to remove all the leading zeros. And that allows us to shorten our address. Now, we could also, if I was just going to take this one step further, I could also shorten these zeros if I so wished, and just leave 1 0 there. Now, no matter how you write out the address, the rules are put in place in a way that you can always go back to the main address. And so you don't have to worry about, you can sort of pick and choose. There are best practices, but the computer's always going to be able to figure it out, okay? Now, the second rule is that successive zeros, or successive sets of zeros, can be removed, but they can only be removed once. So, any sets of successive zeros, and here we see one set, or two sets rather, of successive zeros, can be removed and replaced with a double colon. Now, the reason we can only apply that once is, let's say these zeros we had another set of zeros over here, and we truncated those. We can add up, right? We know there's 1, 2, 3, 4, 5, 6 sets here. So we know that this represents 2 sets of missing zeros. But for instance, if we had, 2 other sets here and we removed those, we might not know whether it's supposed to be 1 set and 3 sets, or 2 sets and 2 sets, and so on and so forth. So we can only do this once, because when we add them back, there's no way to know, where that would sort of lie. Now, I'm just going to erase this for a second, because we can even truncate this more. We've applied this rule, so this applies this rule, this one has applied this rule, but we can apply both rules, right? So we can remove these leading zeros here and actually write this out as 2001 D8 88 A3 double colon, which means that those are successive zeros, 3E 70 7334. Now, I just want to sort of follow up and explain, write out what I was just talking about with why we can't have more than 2 sets of successive zeros, okay? Let's say that we have zeros here as well, okay? So I'm going to rewrite this out. We have 0, 0, 0, 0, colon, 0, 0, 0, 0, colon, 0, 8, A3, colon, 0, 0, 0, 0, 0, 0, 0, 0, 8C, 3E, 0070 7334. Okay, let's first apply our first rule, which is that leading zeros can be removed. So we rewrite this, and we're going to get this. Okay, now we're allowed to remove 1 set of successive zeros only, which is the second rule, okay? But let's do it twice and just see what happens. So let's say we have a double colon here, 8A3, and then we have another double colon, 8C3E, 70 7334. Now, let's say we want to expand this back out to its full version. Well, if we have these successive zeros here, we don't know if this would be written out 0000 dot 8A3 because from what we're seeing here, theoretically, we could put 3 zeros here and 1 0 here, right? Or we could do it the other way around. So the reason we can only do it once is because then mathematically we know exactly how many belong when we do that, all right? So hopefully that helps clarify the reason behind the successive zeros being removed. All right, now what this also means is that if you remember a loopback address, an IPv4, the loopback was 127.0.0.1. Well, we also have a loopback when it comes to IPv6. That's all these zeros to 1. But because we can apply all of these rules, we can truncate this to simply this. All right? So this is important to remember. These rules are important to remember. The other thing I want you to remember is that hexadecimal is 0 to 9, A to F. So they might show you something and say which of these is not a valid IP. If it has a letter, say a G or an H, then you know it's not going to be valid. And here we can check. Here's a D. That's good. Here's an A. That's good. C, good. E, good. So this is good to go, right? If we had an H or a G or an X, for instance, then we would know that the IPv6 was incorrect because there's no hexadecimal symbol X. So the IPv4 addressing method is really different from IPv6 addressing, and it's comparatively it's lacking in many areas. First, as we've talked about, we're using a 32-bit binary address in IPv4 versus a 128-bit binary address in IPv6. And of course, this greatly increases the number of possible IP addresses. I think around February of 2011, all of these IP addresses had been leased, and so there weren't any addresses left. I think we had something where at like 4.8, 4.7 billion, right? And all those were gone. And so we were depleted of all of our IP addresses. So this is why we had to transition to IPv6, because now we have that undecillion address, which again is if there were a trillion people, they could each have a trillion addresses. Now, another major difference between these two is that IPv4 utilized the classless interdomain routing notation, if you remember, which had that slash and then a number of bits. Well, in IPv6, this isn't necessary, and IPv6 actually has a subnet size of 2 to the 64th power. Now, if you remember that the total IPv6 is 2 to the 128, then what you realize is that the first half of the IPv6 address, so if we were to write one out again, let's say 208A, A364, 92BF, 1000, right? Okay, so then we're going to have 4 more on this side. The first 4, which again is the first 64 bits, that's the subnet. So now we've integrated the subnet into the IPv6 address, which is the benefit. Now we don't have to sort of have this extra written out CIDR thing. So it's been standardized. It's always 2 to the 64. We always know the subnet or the network node is on the first section, and the node ID is on the second section, the other 2 to the 64. So this really helps simplify things to a great extent. Now, obviously, one of the issues is we're going to underuse a lot of the addresses. We're going to underuse many of our addresses because we're never going to have to really use this many subnets, or perhaps not even that many networks, right? But there are so many other benefits that it has with routing and efficiency and simplified management that it sort of makes up for it. And so that's why we're going to make that sacrifice. Now, in terms of domain name systems, with DNS, when we talked about, for instance, a google.com going over to, say, whatever that IP address is, I'm making this one up, obviously. It's not a real one because we're in a private IP. But this was called an A record. right? So a server would have something, or a DNS server would have something called an A record, and that A record had this information in it. All right. Now, when we're dealing with IPv6, we're utilizing a quad A record for this mapping. Now, it can also use the same A record, but this quad A record can be used as well. So if you see 4 A's, what we call a 4A record or a quad A record, then you know we're using IPv6. It's one of the differences. And again, these are the records that are used to map IP addresses to what are called fully qualified domain names. Now, while comparing these two schemes also, IPsec, which stands for IP security, is another aspect that we need to consider. In IPv4, IPsec is optional. It's widely used for secure traffic over IPv4 communications. But when we dealt with IPv6, IPsec was designed for it. And so it's required from the original specification, and therefore all communications that are working over IPv6 are automatically falling under IPsec. So it can be considered in some ways optional, I guess, but it is required use from the get-go because it was built into IPv6. Now, the IPv6 scheme can also handle a much larger packet size. The packet size for IPv4 is 65,535 octets payload. When we get to IPv6, we're dealing with a 4.295 billion octets of payload. So obviously, these are a lot bigger. These are what we call jumbograms. As a result, you can imagine that if we want to deal with IPv4 and we're on an IPv6 network, we're going to have to make up for this. Now, if you recall, when we were talking about Ethernet, we also were talking about the header sizes and all the information that was contained in there. Well, the header size for IPv4 and IPv6 is also very different, which actually makes these two protocols not compatible with each other. So IPv6 is not compatible with IPv4. And so the way we're going to communicate with an IPv6 over an IPv4 network, if we need to, is by tunneling the packets. In other words, we take an IPv6 packet, and we literally wrap it around, or we wrap around it an IPv4 packet. And so we tunnel the IPv6 packet inside of the IPv4. Now, this allows it to communicate, but this is also what we call a dual stack. In some cases, we can have what's called a dual stack, where we have an IPv4 and an IPv6, and so we can choose which one to go over, and then this tunneling is not going to be necessary. Now, we don't really want to tunnel because obviously the payloads are so much different in size that it's going to cause all sorts of trouble. So what we'll try to do is create this dual stack in which we have one network and the other, and they're both operating sort of side by side. If we can't do that, then we have to use tunneling in order to move the IPv6 data over an IPv4 network, which might be necessary even if the IPv6 data is traveling through an IPv4 network. All right, so we've compared these. Let's talk about some of the improvements that IPv4 did not have that IPv6 does. Starting with some security and privacy measures. If privacy extensions are enabled with IPv6, then we have something called an ephemeral address, which is created. And this is used as a temporary and random address that's used to communicate with external devices, but the external device doesn't know the true address of the internal device. And so this improves the privacy and security for the user. And this is what we call a privacy extension. And it does have to be enabled from sort of a router point of view. Now, another improvement is a better composition of what we call the unicast address. What this means is that IPv6 uses a unicast addressing structure to replace the classful addresses of IPv4. This offers a lot more flexibility and efficiency with addressing, and depending on the category of the unicast address used, there are different functions for each, meaning that there are different types of addresses that are used, and that way the computer automatically knows what the function is. The first is called a global address, which is sort of like the public or routable addresses in IPv4. If you recall, most addresses could be routed. Those are what we call global addresses. We also have site local addresses, which are essentially like the private addresses or non-routable addresses that are not routable to external networks. If you recall, these were, for instance, the 10.0.0.0 through 10.255.255.255, and then the 172.16 through 32, and then the 192.168. Those are the private addresses. Well, in IPv6, we call them site local addresses. We also have something called link local addresses, which are basically comparable to PIPA addresses in IPv4, and we're going to talk more about what those mean in just a little bit later. But just to give you a little heads up, and we have talked about it with A+, if you were around for that, this is automatic private IP addressing. And we need, because every device needs an automatic IP address, if it's not given one by a server, then it's going to give itself one, what we call a PIPA address. And so in IPv6, these are called link local addresses. And finally, there are IPv6 transitional addresses, which are basically going to be used in the time being until we phase out of IPv4. These are used to route IPv6 traffic across IPv4 networks through tunneling, much like I've just described in the previous section. Now, a mechanism built into IPv6 addresses is a field located in the IP header that's designed to guarantee network resources be allocated to services that need time-sensitive data, such as voice over IP. Right? We need that is time-sensitive because I'm talking and I want the person to hear almost as soon as I talk. And so this time-sensitive stuff is built into IPv6, one of the reasons that we use it. Now, another improvement with this scheme, IPv6, is called hierarchical addressing. This eliminates the random allocation of addresses. So connectivity devices, such as top-level routers, are assigned a top-level block of IPv6 addresses. And then segments are added to those with blocks of addresses that are assigned at that level. So basically, it looks like a hierarchy from an IPv6 standpoint. You remember we looked at this sort of topology earlier. Now, IPv6 scheme also has a much simplified header, and it's going to make addressing a lot easier to read. This improves the speed packet routing on an individual packet basis. So obviously, if we're going to simplify how information can get read, it's going to simplify how routing can occur.